All right, so we're going to get started here. I'm going to get started with the webinar. We have people rolling in. We're at the top of the hour, about 1 minute in. So we are going to talk about today robot and cinemeric control. So using a robot with the cinemeric control and using another tool from our Siemens platform, Siemens NX. So we're going to get into this. But before we get into the topic, I'm going to introduce myself and the team that I belong to, and then introduce our guest speaker today. We're going to have a guest speaker from another department, kind of take over the reins of the webinar and go into detail on what the topic is today. So I belong to a team called the Technical Application Team. This team sits around the United States, so we can get into where we all sit. So we have myself and Adam Caves inside the decks here in Elk Grove Village. We have Brian Baumgartner and Chris in New York, and Chris has the VTAC, so a Virtual Technical Application Center, and then we have Rich down in the Carolinas, and he is our project manager. So this is the technology application team. We have a vast knowledge and a wide array of platforms that we kind of talk about, but really our goal and what we try to do for this team is to take the technology of Cinemeric and show everyone how to use it and what some of those functions are. So we kind of pull from other teams, kind of show you how you can use Cinemeric to the fullest, and that's what we're doing here today. Some of the things that we do training. So we have a DEX USA TAC class and activities. So we have trainings, and you can visit that on our website at CNC4U. We also have the VTAC and content activities. So we do videos almost weekly, if not every other week, on our YouTube channel, Mr. CNC. If you watched every video on this YouTube channel, you would be a Siemens expert. There's a lot of content here. In fact, some of the questions over the years of working with Chris Pollock, I'd be like, how do you do this? He's like, I think I made a video on that. Check the YouTube page. So this is a very good resource if you have a question. There's a little search box on the page when you get to Mr. CNC. So usually if you just put that in there, this is definitely a very good resource, right? Let's say you did watch a video and you're like, man, I wish I knew or understood this just a little bit better. We have a program called the VPE program. So what the VPE program is a virtual product expert. You go to this website, you type in your question, you type in what you want to know, and we will try to get back with you within 24 hours of a meeting invite with an expert from Siemens. It might not be myself, it might be someone else from our team, it might be someone that we pull from a different department inside Siemens, but definitely we have the ability of getting an expert to you to answer some of your questions. Next is Content Manager. You can download this on CNC4U. There's two ways of downloading it on CNC4U. It's in like the first thing that pops up on the page. This has all our YouTube videos with links, as well as all our Cinemeric 1 manuals, our 840D and 828 manuals, how to get a hold of us on our social media, how to join our content list. This is a very, very, very important and really nice document. Also, you can start to search through kind of what you want to know and how you want to cipher some of the information that's on YouTube, on our YouTube page. The next thing is getting involved and getting on our contact list, and that's how you get informed and stay informed with these webinars as well as YouTube Live. So we have alternating months, a webinar, as well as YouTube Live. So this month is a webinar, next month will be a YouTube Live. So this is a way that you can keep you informed and stay up to date. So once we have that YouTube Live come out, we'll send it out to everyone on our contact list. And these are some links that you kind of go through. We have Mr. CNC. We also just started Mr. CNC Insights with Brian Baumgartner, going over service topics, as well as on our Facebook and our Twitter. So we're going to introduce our guest speaker today, Ryan Manning. He comes from 1.5 years at Siemens as a consulting engineer for the additive and robotic machine tool systems. He focuses on machine tools from the digital thread and digital twin creation. And prior to the industry, he was leading engineer for Wire Arc Additive Company. So that's something that he's going to demonstrate today. So without further ado, I'm going to kind of hand over that reins over to Ryan. So Ryan, if you want to jump on and start to introduce your topic here.
Yeah, perfect. Thanks, Dan. Yeah, let me know when the screen share's flipped here. Perfect.
It is flipping. Yep.
Okay, great. Yeah, so yeah, excited to kind of go through this. I have a little bit of a PowerPoint that I'll kind of go back and forth between, but really what I want to focus on is just kind of doing a live screen share. So we're going to problem solve. If anything pops up live, we're going to boot up software live. But basically, what we're going to go through is standing up a digital thread for a robotic system using a Siemens controller. So we're going to go from NX, kind of CAD CAM, kinematic simulation, and then we're going to actually combine that with virtual machine. So the digital twin of the Siemens controller. So we're going to kind of do a software hardware loop per se, and just kind of go through how all of this works. It looks like we have kind of an intimate group, so please ask questions, interrupt. Let's kind of dive into things. I'll keep it high level, kind of end user focused, but as things come up, we definitely have time to kind of dive into the weeds on things. So yeah, without that, let's get started. So the kind of first thing we're going to go through inside of Siemens NX is when we bring in a robot model. So in this case, we have a Kamau robot with a positioner. We're going to bring that in, kind of go over how we assign kinematics. So how do we turn graphics or solid models into actually a working kinematic model, defining axis, defining rotations, hard and soft limits. After that, we're going to kind of go into bringing different end effectors into the cell, what that looks like from a CAM perspective, and then just kind of do a real high level overview of the different operations. This cell is a hybrid cell, so we're doing additive and subtractive and some metrology all in the same work cell just by swapping end effectors. So from a CAM or a tool pathing point of view, we have a lot of options inside of NX. So we'll kind of look at those just real briefly, kind of an overview and what those look like applied to a sample part. The last thing from the NX perspective is we'll look at robot rules, meaning how do we constrain all of the different axes in this system. So in this case, it's an 8-axis system. How do we apply constraints to the tool path where, maybe the positioner stands still and the robot moves, or the robot holds still and the positioner rotates, things like that. The other thing we'll look at is the post processor. So kind of what does the out of the box run my robot post processor inside of NX look like? I know we already had a couple questions even before this started on the post processor on inverse kinematics. We can kind of go through that and look at those results live. So with that being said, I'm going to boot up NX here. So from a work cell perspective, we have Kamau robot with a Kamau positioner and with a numeric CNC strap to it. So a numeric 1 motion controller driving this robot, meaning we're not using the out-of-the-box robot controller. We're turning this into an actual CNC level accuracy system. So we're using G-code, XYZ, ABC to drive the robot. So kind of how do we do that from a programming perspective? And then how does that look like when we actually bring the digital twin of the hardware controller of the numeric 1 into this system? So first things first, we bring CAD into the environment, and then we can start actually assigning the graphics to the tree, or to kind of how this machine tool is set up. So you can see we have a robot base. We assign the junction at the bottom of the robot base. And we can just kind of go through the CAD, right? Joint 1, joint 2, all the way up to joint 6. Doing that, we define the CAD, but then we also look at kind of what does that axis look like, right? What direction am I rotating around? Upper and lower limits, maybe some dynamic properties. And then we can actually preview, right? What does motion of that defined geometry and that axis look like? If you're starting from scratch and bringing in a robot model, right, you can kind of use this template that's just out of the box Siemens NX solution and start assigning graphics to it. if you're using kind of the Run My Robot Siemens portfolio, all of these models inside that portfolio, right? The Kamau, the Autonox, the Mobby, all of those robots are actually already pre-built. So you can grab all of this just from the software website, bring it into NX. All of this is defined appropriately, especially the rotation points. So when you start to get into, right, how is the datum for joint 4 aligned with joint 5, aligned with joint 6, the directions of rotations, those are important when you are looking at building, right, a true digital thread, because I want my digital and my programming environment and all of those values to actually precisely match what my physical machine is. So we can kind of look at the comparison of that when we boot up the controller. Same thing with the positioner. So we start defining, okay, rotation point for axis 1 on the positioner versus axis 2. We get this kinematic tree built, and then we can start actually moving this thing around. So now I know I've taken those graphics, right, moved it into a kinematic model. And so now when I go to simulate, my environment will actually simulate those tool paths and move how I want it to move, kind of mimicking the physical world. So let's look at end effectors. So this cell, right, hybrid additive cell, the way this is set up and kind of the way NX is set up is I can bring in, out of the box devices, right? So I have a whole tree of heads, right, for a robot. Bring in all sorts of graphics out of the box, but you can also bring in custom graphics. Just depends on what you want to do and kind of how your workflow is. In this case, we just have a lot of example heads. We're bringing in a spindle. Maybe it's a laser DED head for additive. Maybe it's kind of more your traditional wire arc, like welding head, or, just a big spindle for machining, probing, things like that. We're going to be focusing mainly on a WAM head as well as a spindle. Now, when we go to toolpath this thing, so we bring in a part into our environment. In this case, right, we have a base plate, and then we have a sample part. So when I look at this part from an additive perspective, using this type of work cell, I know my first operation will probably be a central cylinder, overbuilt because I have some machined areas up here. My second operation, I'm obviously not going to spin the robot all the way around and try to, add this extrusion in this orientation. I want to lay the positioner down, rotate the head of the positioner, and build this extrusion using gravity to my advantage. The second thing would be all the exterior machining. So after the additive, maybe it's a near net shape is built up, we do a head swap, bring in the spindle, and now we start machining some of those critical mating surfaces. The last part would be metrology. How do we probe and inspect this thing in this work cell? Because, I want to make sure, one, I have enough deposited material to machine away, and then two, after I machine, I want to maybe do some in situ inspection before this thing gets removed from the workpiece. So let's look at tool pathing. Inside of NX, we have operations, right? All of your standard subtractive ops, right? Planar milling, multi-axis milling, maybe some blades, some hole making. I know some other webinars have kind of gone through these things, and there's a lot of information on there. What we also have is called multi-axis deposition or fixed axis deposition. Just kind of depends on your machine tool. In this case, we're doing multi-axis. So we have all of these different operation subtypes that have been taken from feedback from industry partners, right? How, with your process, how do you build? What toolpaths do you need? So these have been created, edited, and then released. So these are all released operations that anybody can use. Typical operations, right? Some zigzag infill, maybe some racetrack, things you see on just about every kind of extrusion-based printer. We really get into specifics when we want to do rotary buildup around parts, maybe kind of a free-form additive coating, even getting into gradient materials, right? How are we mixing materials? So all of those settings are inside of these operation toggles. we can look at freeform, which is kind of what we're using for this one. So within freeform additive, we give it a geometry, right? So in this case, it's just that central cylinder. And then we give it a foundation geometry. What are you building off of? Meaning the base plate in this case. And then we can tell it, how do you want the tool axis to be compared to this tool path? So normal to drive, I'm just keeping it normal in Z. So pretty much a 3-axis movement for this tool path. Then we start getting into slicing, right? Do you want to slice the entire feature? Maybe you only want to do a number of layers, or maybe just, a midsection, because I want to decompose this part and do different settings at different ranges through the build. All of these things, profile starts, non-cutting moves, how are my retracts and traversals? All of those kind of what I'll call industrial tool pathing options are now available for additive. So we're not looking at this thing in terms of kind of an off-the-shelf slicer. I prefer to kind of look at it as real tool pathing using a CNC machine tool. In this case, it's a robot with a numeric 1. Same thing with subtractive, right? We have all of kind of a, master cam. There's a lot of different options out there for subtractive. All of those are in here as well. But from a workflow perspective, we would, maybe machine the base plate flat to a known height, build that central cylinder in green, build that extrusion off the side, do some on-machine probing, and then come back in and do some machining. Now with robots, regardless of what operation we pick, we need to apply robot rules and kind of address how all of these kinematics are working together, for lack of a better word. How are all these axes working to bring this toolpath to life? So when we do robot control, we come up with this dialog box right here. So we have all 6 of our robot axes, the 2 of the positioner, and then we have some rules. Rules meaning these are how we constrain the system for this toolpath. So in this case, I wanted to constrain my tooltip to a fixed position. So regardless of where this robot is in the toolpath, the tooltip and that orientation of all of those joints are staying constant throughout the path. Same thing with the positioner. I want constant joint values. I don't want this positioner to move, right? Lock it at 0s for both axes and just let's do a normal, 3-axis build. When we get to this extrusion, things look a little different. Now, instead of, turn on our main part here, right? Instead of being in a 0-0 with the positioner, we have some different dialog options. I can do constant tool axis, constant tool side, constant tool orientation. All of these different options basically let you define how this positioner moves. So I want to lock axis 1 to 90 so that this thing is completely horizontal. And then I'm letting the top spin freely to keep this extrusion. It was off to the right-hand side. Now I want it normal so I can use gravity to my advantage. And same thing. I'm just going to keep the tooltip fixed to a certain position. So we do that for all of these operations. And you can tell when it has a little wrench, that means the toolpath's been edited. My robot rules are applied. Now, the neat thing is after you apply robot rules, we can actually look and validate this toolpath. So if we go, like I said, we're doing this live. So let's see. So if I basically, if I apply the rules to this toolpath, would you like to run a validation? Yes. Meaning now it's going to look at that toolpath and say, okay, what are all of those, let's see. So it's going to say, what are all of those findings for this toolpath? Do we have soft limits, hard limits? Is the robot unwinding? Do we have reach failures, right? So there's a quick way to analyze the toolpath right after you generate it in terms of what is this robot going to do and is it a good toolpath? Okay, so from a simulation perspective, now we have our toolpaths built, we have our kinematic model, we can start actually coming in here and simulating these different movements. For those familiar with NX, we have a couple different simulation options, right? We have toolpath-based simulation, which we're not considering a controller into the simulation. It's purely robot movement, tooltip, following the toolpath. Everything is what I'll call perfect. We also have machine code-based simulation. Typically, this is more of a CSE, so a common simulation engine environment. With the tying in create my virtual machine or run my virtual machine, what this actually does now is we'll use the controller to drive the simulation. So we'll get to that. We're going to start with toolpath base. So I have this on, my simulation ready to go, and I have my material removal, so that IPW, that in-process work piece, is enabled, meaning now I have this blue. So now I can just play and simulate, say, okay, how is this simulation running, right? Am I seeing material removal? Is it cleaning everything up? How are my joints looking? So I can actually come in here and look at my joints. Am I approaching any of my hard limits, soft limits, anything like that, right? Very much software world, very much everything is perfect from a movement perspective. We're not considering anything with the controller, but it's a good first step of, is my toolpath correct? What do things look like? Same thing with the additive portion. We can come in here and simulate toolpath based. Now, all of my operations up to this point are generated, meaning my base plate's been machined and my central cylinder has been deposited in blue. So now if I play this operation, based on those robot rules we applied, now the positioner is sideways, and actually the way that those rules got applied, I'm not seeing any rotation of the top. All I'm seeing is the tool staying normal, fixed in that tool axis. And we're just doing basically what I'll call a 3-axis, just up in Z build, but our positioner's rotated, the geometry has been rotated to keep us in that orientation. Any questions on that kind of stuff before we move on to kind of machine code based simulation? Anything, Dan, in the chat, anything people want to dive into while we're here?
We haven't had any questions come through. So if we have any questions, everyone that's in the webinar, please put it in the question section or in the chat, and I'll be happy to shout it out when one comes in.
Okay, perfect. So let's dive into actually create my virtual machine into here. So we're going to go to machine code based simulation. And what that does is now we have a big power on button, virtual controller. So I'm going to boot this controller. And now create my virtual machine is going to run. This will take maybe 90 seconds to boot. So what I want to do while this loads is actually go back to the PowerPoint here and kind of show what we're using or kind of what's going on. So depending if you're an OEM, an end user, whatever your access level for virtual machine looks like, right? The two options we're using are operate, meaning we have the HMI with the machine control panel, and we're using open. So what we're doing is we're actually using an out-of-the-box Siemens-made open API that hooks into NX, meaning I can now boot, create my virtual machine, run my virtual machine from within NX. And what this does for us is it kind of blends the digital world from a software and from a hardware point of view together. So left-hand side is NX. When we boot up virtual machine, it takes all of the G code for that program and dumps it into the controller. It takes
Ryan, you still there? And we lost you.
Okay. Dan, are we still showing?
We are not. Try to reshare.
All right,
There we go.
So from for those kind of familiar with the back end of NX and kind of how machine kits work, right? So kind of diving behind the scenes, we have the typical kind of layout that an out-of-the-box machine kit looks like, with the exception of now we have a virtual machine file in here. So typically, the way this works is inside the common simulation engine driver, you have what I'll call like the emulator, right, for CSE simulation. Now, we're actually pointing machine code-based simulation directly to virtual machine. And defining that, we can actually tell the system, hey, do I want to run in a create my virtual machine environment, in a run my virtual machine environment, or even in a black box environment? You have a few options kind of depending on, licenses, things like that. So it looks like we are booted up. So let me do a little bit of screen arranging here. Okay. Perfect. Okay. So left-hand side, we have NX. Right-hand side, create my virtual machine, right? So we have the HMI of the Sinumeric 1. And in this case, we have a MCP 1900. So kind of our 19-inch machine control panel. As I mentioned, with that open interface, what actually happens is it dumps over the tool data, dumps over our work offset data, and brings over the part program. Now, the way this boots up right now, I cannot reset this machine, right? I'm still in an e-stop. And that is because the way that the PLC and all of that is handled on this machine is it's actually taking safety into account. So this is purely a kind of a, what I'll call an in the weeds demonstration, but your machine may or may not have that. But within virtual machine, we actually have the ability to look at all of the IO for the PLC project that's in the physical machine. And what I mean by that is, in this case, we have a master operator door reset. So we have some safety. We have maybe a laser lock for the door. We have a handheld pendant with an e-stop and an enclosure. But right now, my whole system is in red because my e-stop hasn't been reset. So we can actually toggle on and off PLC bits that are in the background of CMVM. Kind of in the weeds, but it's kind of a cool functionality. So now that our safety is reset, we're in a bootable and a runnable state. So we can actually come in here and look at the NC code that was post-processed by NX. I know there's a couple of questions on post-processing, so we can, dive into that in a minute. But first kind of thing, we can just start scrolling through here, looking, hey, does everything look right? Great. Let's go ahead and run it. So if we cycle start, just like your operator would at the physical machine, we do a tool change, and now we have a simulation. I don't know kind of how this is showing up in the streaming. It might be a little delayed, but if you notice, we have a discrepancy, right? We're not in perfect software world anymore, where the controller is passing all of the axis positions to the NX model is different than our digital world. Meaning we have an issue between our physical controller, right? So this is an archive from a physical machine, just replicated digitally, and our CAD CAM environment. So now we can troubleshoot. Is this a digital issue? Is this a controller issue? If you're in Create My Virtual Machine and you have access to machine data, we can actually come in here and start looking at our general machine data inside the Sinumeric 1. We can look at our channel data. In this case, because I know what the issue is a discrepancy in this machine data right here, which is actually the positioner data. And what's happening is the rotation point for this joint right here of where the controller is expecting versus where the digital world was created is different. So we're actually raised up a little bit from where this rotation point is expecting. So we can come in here and actually modify machine data just like, someone on the physical floor would. So I can come in here and, maybe bring this down a little bit, restart our simulation, and now we're closer. Now we're lower to the workpiece, actually a little too low. So like I said, we're just kind of doing live debugging. I'm not trying to do smoke and mirrors or anything here, but what I want to show you is that when you're setting up digital environment, you want to make sure your CAD CAM environment matches the physical machine. Otherwise, you'll see errors like this, right? So when you're, depending on how your workflow is, if you're an end user, if you're an OEM, however that looks, you want to make sure that your digital thread is actually seamless. And we can do that, and we can validate part programs, we can validate controller data, validate exactly how our digital system is set up, all digitally without having to walk back and forth between, posting from CAD CAM, walking out to the machine, loading it, running it on the real machine. Hey, there's an error, walk back to the CAM office, right? We're doing all of this digitally. So I can reset here. Let's restart this program and see if we did it. Okay, that looks a little better. So what's happening here is we have an M74 active and then an M75 active. And that means deposition on and deposition off. So how does NX know what the controller is sending back and forth? I'll open up TIA Portal. We can look at the PLC logic and actually show that NX is reading PLC logic from this controller to pass simulation on and off. Before I do that and boot up another software on the laptop, there's a couple questions on, let's see, post-processing, robot configuration, XYZ, ABC. Okay. So I'm going to stop the controller, reset. Let's finish the simulation. What's nice is when you boot this once, it stays in the background. So let's look at the post. So for this particular part, right, we're doing just a central cylinder. With our robot rules applied, we are constraining the tooltip in this position. So right now we're in kind of like a joint view. When we turn the transformation or Traore on or off on the sinumeric, then we go into a Cartesian, right? X, Y, Z, A, B, C. The post configurator, the post processor is going to take your robot control, so how I constrain the system, and turn that into G code. So if we dive into the post and look at this, it might make a little more sense. Okay, so this is completely out of the box, right? This isn't anything super special. If you want a robot with a sinumeric controller, so full Siemens thread, it's here for you out of the box. If we look at robot settings, this is where we kind of define our ABC rotations. So I define what are my joints 1 through 6, and then I can actually look at the orientation of the angles, right? X, Y prime, Z double prime. Maybe it's backwards. Maybe it's X, Y, Z, Z, Y, X. There's 3 options really. This is where, again, your digital and your physical systems have to match. So inside the sinumeric controller, there is machine data that define this orientation of how the ABC is interpreted by the controller. But what's nice is we can debug and create this solution digitally and test it to see actually what is the controller expecting versus what am I giving it. So what I can do here, I'm just going to change this to RPY. So now instead of X, Y prime, Z double prime, we're just in RX, RY, RZ. Okay. Save it. This operation is still highlighted. I go simulate machine. Machine code based simulation. If you see on the bottom here, it says sub post process is running. So what it's doing is it's reposting that code. So we just made one toggle switch in our post processor, but it's reposting that code. And it's going to kick it into our controller. Probably could have picked a lighter program. Okay, perfect. So another application has changed this file, meaning we just kicked a new code in here. Okay, click OK, reset our machine. And now let's run this new code and see what it looks like. So we just saw that it worked perfectly. We did one different ABC toggle dropdown on our post. Okay, so in this case, it still works, right? We're the way the controller, the way that the post output with that different dropdown, because we're really in an ABC, right? The controller's not throwing any errors. There's nothing different that it's expecting. We get into some kind of multi-axis with the positioner dropdown, we might see something different. So we can look at that. So right now we're in ABC 35. Okay. Let's go to post configurator, open this back up. Let's change this maybe to our third orientation dropdown. So now we're in Z, Y prime, X double primes, right? So opposite of where we were first with our X, Y, Z. So we click OK, go back in here. We're going to repost that code and kick it into our physical controller. So what's nice is, I mean, before I was at Siemens, I was using this thread without virtual machine on, factory floor. And everything looks great from a CAM perspective in software. But when you actually bring that G code out to the controller or when you give it to the operator, it was a constant iteration of back and forth of, hey, I'm seeing this. Hey, can you change this? Hey, the controller, is throwing an error on this. There was a lot of just wasted downtime and a lot of kind of hesitation on what was the robot going to do versus what my CAM environment said it was going to do. And this really just takes all that away. Now you have a physical archive from the numeric on the shop floor. You have the real PLC logic running in the background. You have cycles, tool changes, anything like that running in here. And you know what the controller is doing and what it's expecting. Okay, so here with that new post change, now we're actually in A35, B0, C0. So if I cycle start this, my tool is completely different, right? Now we're at a completely different angle. We're not normal to the surface. And that's how fast and how easy we can iterate and actually define the tool path changes, the post processor changes, and validate what this is going to do. Does that answer a couple of those questions? I'm hoping from kind of the ABC perspective. The other things we can look at in here inside the robot post, because that's always the question, is how do you map kind of maybe those external axes? So we have 6 out of the box positions, right? So this thing could be robot 2-axis positioner on a rail, hanging from something, right? So you have all these different degrees of freedom that are in the Run My Robot kind of out of the box application that we can define. Same with the base frame and the tool frame. Like, where is this positioner rotating versus where is the top rotating? Are we trying to do coordinated motion, or are we trying to do robot motion is on its own, positioner is on its own? There's no transformation defined in the controller. Other things we can look at here from an additive perspective. So if you guys are, right now you're using subtractive for your machine, you want to maybe strap a welder on and do additive, you can just add a layer into your post processor from post hub. It's pretty much that simple. You just grab it, add it in, and now you have these different settings for DED, FDM, WAM, and it just lets you really customize your post, but it's all out of the box. What I'm looking at here is deposition output, meaning from a PLC, from a machine-based perspective, what is turning on and off the additive head, right? So deposition on is a 74 and off is a 75. So if I look at my G code, that's what I see. So start a program, I have a deposition off, make sure the welder's off before I get to my start position. And then now I have a 74, deposition on, and now we get into our XYZ ABC movements. Kind of what I want to show, and I think this is a little bit in the weeds, but let's dive into it because we said we'd hook up TIA portal, is I want to show how this interface really translates M commands from the controller and makes it happen in the NX environment. So let's let this boot up here. Come on. I guess in the meantime, I can boot up. Okay, here we go. So inside NX, when you're configuring all of this, kind of this interface, is we have subprograms. So I have 3 subprograms here. M74, meaning when the controller kicks out an M74 in the G code, I want to, and this is just any command language. It's kind of just the basic, back end of NX simulation. When M74 is triggered, set the tool mode for my tool, which is a laser, to add material, meaning deposition shows up. Same thing. When an M75 is triggered, set that tool mode to off. If we look at tool change, numeric tool change is an M6, and this is the command behind it. Happy to kind of go through it a little bit, but basically what it's just saying is when an M6 is triggered, depending on what tool is brought into CMVM, you're going to grab the head or the end effector of that tool. So if you have an end mill, grab the spindle head. If you have a deposition laser, is what I called it, grab the WAM head, right? So knowing that now, if I run this program and I'm looking at my auxiliary functions here that the controller is interpreting, now when an M74 is triggered, I have set tool mode to on, right? So deposition orange, M75, turn it off. So that kind of makes sense how that works back and forth from a CMVM to NX perspective. Now, what I'm going to do is boot up TIA portal. So this is the PLC program behind the physical machine and behind the CMVM. So this controller right here. Any questions or anything in the meantime while this takes a minute to boot up here?
We have one question in the chat, Ryan, and it's kind of a sidebar question. It says, robot manufacturers, are they integrating Cinemeric 1 controllers like on an ABB or a FANUC?
Okay, let's see if.
Like, are they using?
Okay, sure. So, yeah, a little bit of a sidebar question. So I will answer the Siemens. So Siemens has a run my robot portfolio, meaning there are 3, now 4 manufacturers, Autonox, Mobi, and Kamau, that are in a partnership with Siemens to integrate Numeric 1 controllers onto the system. Meaning from a commissioning perspective, all of the inverse kinematics, all of the calibration, all of the joint positions and linkages, all of that data has been pre-configured for a sinumeric controller. So you can stand up, commission, put a sinumeric CNC onto those 3 robots, all of their models, and have a very, very accurate CNC robot. Could it be done with other manufacturers? I'm going to say yes. The sinumeric one could drive any cast iron, right? Where you're going to run into time and money is, can you get the inverse kinematic data from the robot manufacturer? How long does that take to calibrate, integrate into the sinumeric one controller? And just kind of like, what level of investment are you willing to kind of do to then do maybe like a more transformations on top of that to increase the accuracy, like an iSIOS calibration or something like that. Yeah, here, let me oh, misspelled there. Okay, so those are the 3 that are in the Run My Robot portfolio right now. We could probably have a whole other conversation on Run My Robot and what that looks like, but I'll just kind of leave it at those are the 3. There's Collateral, where you can happy to share the whole list of what all the models, the payloads, the accuracy, all of those data sheets for those robots. Dan, that might be something to take note of.
Yeah, we can also put that in the list of when we put this up to YouTube. We can put it in the description.
Yeah, perfect. Okay, so what I want to show here, so this is the TIA Portal project for Create My Virtual Machine. So whether you're commissioning, an OEM from the front end and you're trying to kind of commission a system commission a system digitally, you can actually write all of your logic, test your button mapping, all that kind of stuff digitally. Same thing as, an end user. If you have access to this, maybe from an additive perspective, your PLC project is 90% done and you just need to integrate the end effector IO into the project, right? You can start mapping that out digitally as well as testing it physically. So just like a real machine, I'm going to go online, right? So maybe you're in the field, you plug into X127, X120 port on the CNC. Same thing here, except we're mapping it to the local address. So so 127.0.0.1, that's our CMVM local address. So we're going to go online. We're going to find the NCU that is in our CMVM digital twin. Okay, so go online. And so now what we're doing is we can have a connection, right? So we're green on the whole left-hand side, meaning, except for this one, but meaning that our PLC project inside of CMVM is now being read by TIA Portal. So we're online and we're watching stuff happen live. So if we come in here and monitor this block, you know what? Let's just do this. Let's just download to the device. So there's an update I made in the PLC project that's not currently active in CMVM. So just like a real machine again, right? We're going to download to our device. So I'm going to load it. And now we should go green. Okay, so now we're active. So now I can monitor this. And this is what I want to show. So right now, if I go MDA and just type in an M code, let's do M75. And I cycle start. Okay, so I just turn the laser off. Now, if I come in here and do M74, cycle start, laser's on, meaning now, I don't know if you guys saw that, this logic right here just went hot. So my macro for my laser on is on, and now my output Q00 is hot. Okay. So keep that in mind. So now I have a hot output Q00. If I'm inside of NX and I actually look at the logic for turning the orange bead on and off, what I'm doing is I'm reading the variable Q00 from my PLC program inside of CMVM and using that to set my tool mode on and off. So as the IO gets triggered in the PLC backend, NX is making it happen from a simulation perspective. I hope I made that kind of as clear as possible, but that's essentially what's happening, right? Is we're using NX to read PLC logic of this digital twin of the Sinumeric 1 virtual machine controller, and then we're using that to turn deposition on and off. So if I turn this off, now we're not hot anymore. If I go to auto and just run this, you'll see, so just watch the green on and off as my auxiliary function on the controller goes on and off. And then in the background, NX is doing the exact same thing. As stuff goes hot and goes off, my orange bead is turning on and off. Kind of cool functionality, maybe a little bit in the weeds, but I thought, it's important to show that it's real, right? It's the real NC kernel on the physical machine, and it's your real PLC project in the background running. So I'm going to turn this off just for bandwidth here. Does this support Danobat? I know at the JEC World Conference a few weeks ago, Siemens and I think Danobat who released a new robot model. So yes, this will all support that once that machine tool robot hits American shores. Okay. So we kind of did additive, showed how the M codes and all that kind of stuff work. We're kind of coming up to the top of the hour. I can quickly go into this last kind of portion that I had, which was how we can actually do probing and do kind of a closed loop feedback from CMVM to NX. Or we can kind of dive into some more questions. Dan, you let me know how we're doing.
I think you're doing good.
Okay.
If anyone has any questions, I say keep rolling through the chat or the question section. I've been monitoring them, and you've been also seeing them too in the chat. So, yeah, I mean, I'd say keep going.
Okay. All right, let's do it. So, let's talk probing. So, on-machine probing is a way to do offline probing cycles inside NX. Meaning, when I have a Sinumeric controller, I have certain cycles that the Sinumeric inherently has to do different probing cycles, right? So cycle 977 is a circular spigot. Maybe I'm measuring the exterior of a circle. Maybe I want to measure and then set my origin to the dead center of a circle. This other one, right, maybe just an outer circle segment. So when we do offline probing programming, we can actually grab the geometry and let it know, so in this case, right, this is my geometry. I just grab the outer surface of my cylinder. This is my theoretical as deposited thickness. And what it does is it says, okay, these are the two Sinumeric cycles that are applicable to that geometry, right? And so for 977, I can actually come in here into the option tree and start defining parameters. How high do I want it to retract in between probe points? How much engagement do I want? Do I want it to just be a measuring cycle, tool offset, things like that? I'm going to kind of go through this quickly for time, but now we can actually simulate this cycle inside of our CMVM. And when I say that, what I mean is we can use the IPW, or the in-process workpiece, as actual probe points, which CMVM registers. So when it's a collision between the probe and my in-process workpiece, the controller is registering that as a hit, and then that is what it's using to do the calculations. So kind of like we did before, if I start, oh yeah, that didn't kick out right. Okay, well, like I said, we're doing live, so let's switch it up a little bit. Let's do a different probing program. So what I did beforehand is I actually wrote a probing program that runs actually through 3 subprograms. So it does an exterior, an interior, and then probes some points. And that is what I had active here. So you can see we have 2 interior diameters in yellow, 2 exterior diameters in red, and then a few probe points. So what I'm going to do is actually run a tool change here for the WAM head, set some machine data on the controller for the tool point for that WAM head, and then I can start actually running this program. If it works. All right, sorry guys, debugging while we're doing it here. Anyways, really the motion isn't important. What I want to show is how everything interacts from a CMVM to an NX perspective. So what I mean by that is, assuming, right, I ran my probing program and I kicked out a CSV that has all of these different data, right? My part height, my probing height, interior diameters, and then the location of all those XYZ probe hits. The way that this CMVM is set up is I actually mapped a shared drive of those results to my desktop. So I'm in a local network. Maybe, you know, you have physical machines, everything's mapped to like a shop network, something like that. But what I can do is I can actually access those probe data from Create My Virtual Machine. So this right here is the exact copy of what is on my controller, right? So mapped drive of the data results, and I can pull it up inside Excel. With that data, I actually mapped a NX routine that takes all of those points as expressions, creates diameters, creates probe points, and overlays it onto the model in my environment. So to show that this isn't just smoke and mirrors, what I'm going to do here is make this, I don't know, we'll go 350 as my part height, right? And I will close this, and then I'm going to import my probe data. So now it's reading the values from that shared drive and updating my CAM environment with those values. So now all of those values raised up to 350. If I bring this back to 325, and, you know, from an additive perspective, maybe as I'm going around this circle, a bead fell in or had like an arc shortage, something like that, right? So if I make this maybe 100 instead of 94, and then reread in my import probe data, let's see what happens to those points. Okay, now we're looking at all these points. Right here, that point right there now actually is adjusted off of the interior diameter because that's where my probe result hit. Right, so now, okay, I don't have enough material there to machine. Maybe we need to add some with additive. Maybe we need to mill it back down and rebuild, etc. All of this is to show that your offline programming and your workflow with data and probing it all can be combined, right? We can test out our probe programs, test out how is our synumeric mapped to the network, how are we getting data back into our CAD CAM environment for analysis and like for the next decision of the build. All of that can be done digitally. Hope that makes sense.
Yeah, Ryan, that makes that makes really good sense. I had a question as you were starting to do this. Like,
yeah,
what would be the reason for this probe data going back into NX? But I think that is a good way of presenting the information back to NX for subtractive. So if you were going to do, you know, additive and subtractive, that makes total sense because like you said, I'm assuming in this additive subtractive world, there's a lot of machine add to make sure that when you're going to do the completion of machining, that you have a complete part to what you said. Otherwise, if you didn't do what you just did, you're flying blind, hoping that the additive was where you said to go.
Exactly. And so, right, this is probe touch points. The more popular route would probably be a 3D scanner, some other sort of NDE, but same workflow, right? Just take that data, push it back into the environment, and if we're looking at our operation tree, right, we start with additive, we probe, and then now we're doing finished machining, assuming from an analysis, and NX has so many different analysis tools, but we can look at the wall thickness of the probed data or the probed model or whatever you bring in here compared to what you're expecting, and let the operator, the programmer, or even kind of more of an AI thing make the right decision of, can I move forward to the machining step, or do we need to back up and really figure out what to do with this part before we get to the machining step. So yeah, kind of incorporating additive, subtractive, and metrology in one work cell has a lot of advantages.
Cool. Yeah.
Yeah. Let's see. How do you configure multiple robots with a single turntable? Okay. Let's talk about that one. So a couple different options from an NX side of things. I guess really it depends on what the physical system is set up as, right? Inside the numeric, we have channels. So meaning I have if I look at my machine data right here, I have 6 axes, 7, 8, 9. So really I have 9 axes assigned to this channel. If I added a second channel to this numeric 1, I could drive 2 robots and the positioner in with one motion controller, with one NCU, right? Maybe you hit some processing issues depending on how complex your CNC motion is, but that's one way to do it. One numeric 1, 2 channels driving multiple robots. From a programming perspective, you can absolutely do that. You can actually bring the second robot in here. You can coordinate weight and go marks between the robots, so there's coordinated motion. There's an out-of-the-box solution, actually. Okay. Separate numeric 1. Perfect. So I actually just finished a project this week with that. It's actually 6 robots in a single work cell, 6 numeric 1s, all having ROCO. So the way that would happen, if you wanted to use this exact same workflow, because think about each robot will probably have some NC data that's different, right? Whether that's tool position, whether that's location of the robot, etc. You can actually map and boot up each robot individually to their own CMVM. So if I wanted robot 1 with its CMVM to be active and do, CAD CAM CMVM kind of tool chain, that's great. I can boot it down, and then I can boot up robot 2 with its attached CMVM controller with its specific machine data and go that route too. It's absolutely all possible and all works in this kind of out-of-the-box tool chain. If you want to get into more of I'll call it like high level PLC logic, right? Like maybe you have a master PLC running cell safety on top of multiple robots, all with their own numeric 1. You could use Mechatronics Concept Designer. You could use Technomatics, a couple options there. But from an NX manufacturing perspective, right, we're concerned about individual machine tools and tool on part, not exactly like monitoring cell and automation, if that makes sense. So yeah, that's really all about I have in terms of this workflow. Numeric 1 controller, NX manufacturing, NX multi-axis, and then virtual machine. It's all out of the box tools. It's all there for you on being able to really take your simulation to the next level and to the next kind of comfortability by using the real NC kernel, the real machine data, and the real PLC logic to drive your CAM simulation.
Nice. I think we covered all the questions. Anyone else have any other questions? And this is all you had, right, Ryan? We're towards the end of everything.
Yeah, this is all I have. I think there's an open question. I don't know if it got answered for EC where you teach robot configuration or turn. When you strap a numeric controller onto a robot, now you're looking at it from a CNC perspective and kind of out of like a robot pendant robot controller perspective. When I say that, what I mean is we're not teaching. I mean, you can teach points, you can teach positions, but we're not exactly teaching points and teaching configurations like you would with a typical, like I'll say a kind of a production robot, right? Doing the same thing over and over. You're using your CAM environment and treating the robot as a machine tool. So when I'm applying these robot rules to kind of say, how am I configuring this robot during this entire tool path? I can absolutely come in here and pick, a different configuration, right, of the joints, the wrists, arms, all that kind of jazz. So it's more of up to you as the CAM programmer of, what am I going to pick? How am I going to position this robot with very, fast feedback of, hey, this isn't exactly a good position because you're hitting joint limits. So this is, I would say, where the configurations would be taught and where all of those kinematics and points would be taught. But we're thinking about it from a CAM NC machine tool, not really like a robot teaching pendant perspective.
Cool. We had a few other questions come in. Is this for 840D or just for Cinemeric 1?
Yeah, so create and run my virtual machine are Sinumeric 1 focused products. 840D has a very similar thing called VNCK, so Virtual Numeric Controller. It's very similar to this, not as much functionality, doesn't include the PLC logic in the background for this digital environment. But you could do it with an 840D, or if you're an OEM, even looking for to like what is an upgrade from 840D to a Cinumeric 1 logic, like how does that look like? You can do all that here digitally and actually do that upgrade, do that commissioning, and write your logic, test out your button mapping, etc. So there's a few ways you could do it, but VNCK would be kind of the 840D compatible software.
Do I need TIA Portal to do all this?
Oh no, that's a very good question. So I think I put a screenshot in here. So for people that are familiar or not familiar with virtual machine, if you boot up Create My Virtual Machine standalone, right, and you say, okay, I want to, maybe you're an OEM end user, whatever, I want to make my own, create my virtual machine of my physical machine. You can actually create a new project using a generic PLC, and inside that PLC will basically handle whatever machine control panel you want. It'll also handle all of this M code or H code passing back and forth between NX and CMVM. So if you wanted like the fastest way of how do I stand up my physical machine and connect it to my CAM environment, you would do a generic PLC. You would take an archive from your real machine, dump it in there, and then there's a couple like simulation environment variables to change in the NC, but essentially like you're set and you're ready to go. So you don't need TIA Portal, especially as like an end user. You definitely don't need that.
And then one of the last questions, and we'll wrap it up. Is there a tool change limit to the robotic and additive systems?
Is there? Sorry, can you say that again?
Is this tool change limit
Oh,
to
oh,
just robotic or additive system?
sure. Yeah, no. Robot is purely the cast iron with, you know, the glue gun strapped to it in this example. Maybe it's a 3-axis, 5-axis gantry. Maybe it's a robot hanging upside down from a gantry. Right. The machine tool itself doesn't matter. Um, for this workflow per se, just this example was using robot and then a controller configured for run my robot.
Nice.
But yeah,
And
absolutely could be a gantry.
there's one more that came through in the chat. It says I have create my virtual machine and run my virtual machine, but I don't have any robots. How do I get access to that?
To the robot library. Okay, so there's a couple options, right? Inside of Post Hub on NX, there are example machine kits with Mobby robots that match exactly the sample robot programs inside of Create My Virtual Machine. So if you're in this screen, right, create new project or even open a project, you can download sample projects right from the software website. Instead of sinew mill, all that, right after this are robots. So there are out-of-the-box virtual machine examples with robots, and then there are also NX examples that match that environment. So all of this has out-of-the-box kind of samples to play around with and see how it looks.
Nice. Thanks for that, Ryan.
Yeah.
Well, I appreciate you coming in and speaking about the robot NX and additive. It was a great one. I learned a lot. I definitely have had most of my career doing subtractive, so this was kind of cool to kind of see how NX handles additive and well as Create My Virtual Machine showing that too as well. So that's really kind of a good, a very good demonstration and something nice to add to our YouTube channel as well as this webinar. So I appreciate you coming on and being a guest speaker.
Yeah, absolutely, Dan. Thanks for having me.
All right, well, we're going to end the webinar here, and I appreciate everyone coming out and look forward for the video to be sent out after this webinar is finished, as well as I'm going to upload this to our YouTube channel. Thanks for everyone that came out.